Yeah, okay. Ladies and gentlemen, are you ready? Yeah! Okay. Yeah, are you ready for what? Yeah, for our talk, Brain-Computer Interfaces Demystified. Can your thoughts take over control? So this is the question, and hopefully this talk gives you an answer. So today we want to talk about different brain-computer interface devices, like for example this one, the OpenBCI, the Epoc, and NextMind. Yeah. Before we start, we introduce ourselves, as always. So please, Thomas.
So my name is Thomas Endres. I studied computer sciences. After my studies, I joined TNG Technology Consulting in Munich. And for the last 8 years, I think, we have been working on innovative prototypes together with the TNG Innovation Hacking Team, and this is now one of them. But we also were at JFOL, for example, with our deepfakes, with I think the Avatar project.
I'm not sure. Maybe like the audience knows. I don't know.
All right. So Martin.
Yeah, my name is Martin Förtsch. I'm working since 15 years for TNG Technology Consulting. They are based in Munich, Germany, and yeah, let's continue with Jonas, because he's really new. It's the first time at the JFOL. So welcome him here, please.
Thank you. So hi, my name's Jonas. You can see I also have like all these beautiful awards that the other two guys have as well. And I'm not going to tell you too much about myself because we're going to be unrolling my story.
Yeah.
Now.
The nice story, how Jonas came to the Innovation Hacking Team. It was once upon a time, little Jonas. Yeah, he's a huge Star Wars fan. And yeah, he was at a conference and he was seeing all those showcases we are realizing at TNG. Yeah, so Thomas met Jonas, and he was showing all those showcases we are realizing all the time. And you may ask yourself, which showcases? This one, for example. We started in 2013 with 3D cameras from Intel, Leap Motion and stuff, and we tried to control real-world objects with bare hands. Later, we realized this prototype, the so-called Terminator vision. With this Terminator vision, you can see the world through the eyes of a Terminator. Yeah? Very important feature is if someone looks into this Terminator vision, there is some kind of emotion detection. And the wireframe is highlighted, and when the light condition was really good, also the pulse rate was really cool. Yeah, we worked with HoloLens, with some here, this Now robot with gesture control, and so on and so on. And Jonas, he was really, yeah, Thomas, do you want to continue?
He was already amazed when he saw all these different showcases, but then we also gave him a handout and we told him, yeah, you can work for our company. And that was quite convincing for him, but we still had one thing that we could offer him, and this is, of course, sugar. And sugar not only in the form of candy, but also in the form of interesting projects, also somehow related to Star Wars, maybe. And we now have a schematic of how it looked like when Jonas was really taking in all this information. And then he really started to work for TNG. And I think you're still a Star Wars fan, right?
Yes, so one thing hadn't changed over the years. I was still a Star Wars fan. And the thing I'd realized by then was that it's not going to work kind of with the Force. I'm not going to be able to be a Jedi. But maybe we can still move things around with our minds. And then we had the idea. So in the past, Martin showed you, we've been controlling drones with gestures. How about we control drones with thoughts? And that's how this entire BCI idea came about. And we started doing our research whether this is even plausible to do. And we found this beautiful video from the University of Florida. And what you can see here is, well, we have a bunch of drones, we have a bunch of students wearing weird things on their heads, and it seems like they're kind of controlling these drones only with their thoughts. And we saw that, and we thought to ourselves, wow, this is great. Maybe we can do it even better. And this gave us all the motivation that we needed to start off this very much Star Wars-inspired project. So what are we going to be talking about today, Martin?
Yeah, let's have a look to the agenda. At first, we start with a short history overview, then what is a BCI, what is electroencephalography, EEG, control signal generation, fields of application, and last but not least, a conclusion. So a brief history of the BCIs. So actually, Hans Berger was one of the first scientists discovering the EEGs, and it was in 1924. So what did he actually discover? It was that he discovered that there is electrical activity in the brain and that you can actually measure that. So how does it work? So let's remember the school when the biologic lessons. So we have the nerves, and there is the action potential, and if there is a threshold, then this action potential will be there, and there is and you can measure that actually with some kind of sensors on the surface of your head. So this is the first paper where such recordings were published by Hans Berger, and if you have a near look, it's 1929. So he was not publishing this stuff because he wasn't really sure if this is really a thing he discovered there. So what we have here is 10 Hz sinus control wave, and here the alpha brainwave. So there are different types of brainwaves existing. The alpha brainwave typically is from 8 Hz to 12 Hz. Here we have the sinus control wave again. Then we have the electrocardiogram, and here the beta brainwaves, which are typically from 12 to 38 Hz. So when Pierre Gloire was translating the papers of Hans Berger, there was a quote, and he said the publication in the 1920s of the first paper on the human electroencephalogram by Hans Berger was an event for which the scientific world was not prepared. You can measure your thoughts, oh my God, unbelievable. That's not good. Yeah? There is the so-called Berger effect. Brainwave types are influenced if your eyes are open or closed. So you actually can measure that. If your eyes are opened, you typically can measure so-called beta brainwaves. If you close your eyes, you can measure alpha brainwaves. Then they will change to those with 8 Hz to 12 Hz. If you open the eyes again, beta brainwaves will be measurable in this case. So how many different types of brainwaves are existing? So here is a short overview. So with less Hertz, they're on the bottom. So like delta, this is if you're nearly dead, or at least deepest mediation state. Then we have those theta brainwaves, 4 Hz to 7 Hz. You can see vivid imagery, thoughts beyond consciousness and stuff like that. And typically you're in the alpha if you're relaxed, beta if you are solving some tasks, yeah, and gamma, this is multitasking. So you probably are having right now beta waves just by listening to us.
A few of you might have alpha waves or theta waves.
Maybe.
From the looks I get.
Yeah. The first EEG machine was built in 1934. And actually, this was a Western Union telegraph, a modified one. And with this, it was possible to record such brainwaves for the very first time. Yeah, Thomas, what about media?
Yeah, within the media, we also had vivid images of how such a brain-reading machine could look like. So this is from the year 1955 from Flash Gordon, the brain machine. And in this case, it was not a device with which you could read out the thoughts of a human being, but with which you could just eliminate it or delete it from the brain. But as you can see, they always imagine it as some kind of head which sits on your head, and then you can do things with your brain on that, with that. And we'll now have a closer look of how this looks in a modern brain-computer interface. So, but before we can start having a closer look at the concrete devices, let's just see the theory around it. And the term brain-computer interfaces was first termed by Jacques Vidal in the year 1973. And here you can see all the steps that are necessary for really getting from the human on the one hand to the application on the other side. And there we have, for example, for the first time we need to do some data acquisition, then we need to pre-process it, filter it a little bit. Then we can do some feature extraction from the clean signal. We can classify what we have so that we can know what the person is thinking about. We can then put this into the application interface, and then we get the control over the application. And what we'll have a closer look at today is, first of all, this part, the data acquisition, and this is the EEG part. And then we also have the control signals generation, which happens up here. So what can you do with modern brain-computer interfaces? We found a video from 2008, and we are not huge fans of animal testing, but it was quite amazing what they were able to achieve with that. And this, you can see this here. So the ape in this example is not able to move his hands. So he has to use his brain power to get the machine to bring him the banana, and so he can pretty closely really take control over the robot hand to give him this banana. And we thought that if this is possible with modern technology, we should also have a look at what we can do with different types of EEG. So what is out there, Martin, with all the different EEGs that we have?
Yeah, at first we have to differentiate between different invasiveness types. So we divide between non-invasive, partially invasive, and invasive electrodes. So let's have a look to Neuralink. So this is a company where Elon Musk is somehow involved, and it's a fully invasive BCI. This means you need a surgery to get those sensors implanted, and yeah, that's a cool thing. But there are so the idea for Neuralink is to place the sensor actually there where some centers of control for different things are happening. But there is also some kind existing like partial invasive sensors. So this is there is also the need to open your skull, but you will place the sensors on your cerebral cortex. Yeah, and the problem is, yeah. Let's open Thomas' skull, so he was totally against that.
Yeah, let's put it like that. Jonas was a bit excited about it, but I was not really convinced up to the point. And I found this lovely page where you can also buy some non-invasive BCIs, and I put it like that. We should first try the other alternatives. And there is a wide range of devices that are out there, actually. And we concentrated on the consumer market because you can really buy brain-computer interfaces or EEGs for hundreds of thousands of US dollars. These are quite good in the sense that they really have a superior quality of data that you get, but they are also quite expensive, of course, and they are normally just used for medical applications. So what we did, we had a look at all the consumer electronics that you can get for a reasonable price. And there's, for example, it starts with a pretty low price of $99 for the NeuroSky Mindwave. But it also has just one channel, so it just measures your brainwaves from one point on your skull. Then there's also others like the Emotiv Insight, which we saw in the video for the University of Florida as well, with 5 channels. And there are the 3 ones that we are talking today. We will take a closer look at each of these in the next few slides as well. But as you can see, the prices go up pretty quickly. With the OpenBCI, we already have something like $2,500, so it's not cheap as well. And at the same time, look at this amazing quality this headset offers you.
To hear that.
So, yeah, that's pretty good. Okay, but let's dive into a few of these devices. Emotiv Insight, so this is the one from the video before, and as you can see, this is what it looks like. It has 5 electrodes which are sitting on your skull, and to really get a meaning of where they are sitting, we should have a look at another point of theory, and this is the EEG 1020 system. So this is a system of where we should put electrodes on your head to really get the most out of the information that is available. And here you can see different areas of the brain. The blue region is the prefrontal cortex, so this is where high level thinking is happening. Or for example, we also have the red area. This is the visual cortex, where the information from your eyes gets processed, and so on and so on. And we then just take the distance between the back of your nose and the back of your head. Divide that by 10, so we have every 10% of the way, we can then just put 1 electrode. And then we go around this line and put some circles around it. And at the end, we will just need 5 electrodes if we go to the side. And the closer we get to the center, we will have more electrodes there. And this is where we can put the electrodes, actually. And so when we come to the Emotiv Insight, this is these are the points where we will put them. So there are a few in the prefrontal cortex, which makes sense because we want to get that information probably. And there's also some near the visual cortex as well. So that's good, but as the common saying goes, you cannot replace electrodes unless you have more electrodes, and this is why we had a look at the OpenBCI.
Yes, the glorious OpenBCI Ultra Cortex 4. We have it here, and you also see it here. So, yeah, OpenBCI in general, it's like a BCI initiative, so they take care of BCI problems, do all kinds of stuff. And as you can also see, it's a 3D printed helmet that has a couple of sensors here. And we have the version that you also see right there that uses like the, it's called the Cyton Daisy board, that has 16 channels, that means 16 electrodes, and it transmits its signal via Bluetooth through a dongle that you should not lose because it's quite expensive, and that would be really stupid. And since we don't have like an invasive BCI, we have to have some kind of other form of contact, and in this case we have it through, well, so-called dry electrodes. So you can see them right here. They kind of look like little metal combs, and this means that those will contact the scalp directly. Why are they shaped like combs? Well, what do combs do? They go through hair, and they also kind of create these beautiful, very little surface points that will just dig into your scalp and make sure that you have very good contact. And of course, this becomes a lot easier if you don't have hair, such as Martin. And we're just going to have a look at, well, the OpenBCI on him. And you can see on first sight, well, it has a pretty good coverage of like basically the entire upper head. And another thing that you can see, it looks quite hacky. And we like that, so that's good. And it also comes with a couple of very fancy, beautiful accessories like those little ear clips here. And those actually serve a purpose too. They don't only look good. This thing runs off battery to reduce noise, and the ear clips are kind of the ground wire here to complete the circuit. Yeah, and if we have another look at the EEG 1020 model, you can see, yeah, it's pretty even. We got quite a lot of electrodes here. It's 16 sensors once again. And if we were more interested in like one particular area, we could even place sensors in these locations, even though we only can do 16 at a time. And the OpenBCI is just not a bunch of 3D printed hardware. It also comes with a heap of software. For example, the OpenBCI GUI that you can see just here. And this allows you to, for example, monitor your brainwaves. That's what you see on the left. And also do like some frequency analysis. We'll see why that is important later on. And then also like this very cool head plot. Like we've been working with this thing for like a year. We have not figured out what it's good for, but it looks kind of cool. And then there's also the BrainFlow API, which means that you can now read your EEG data in code. And it has like APIs for C++, C#, Java, and also Python. And this means that we can now read brainwaves in a live presentation. So let's have a look at that. And you can see it kind of doesn't look at all like the ones that we saw before. So it's pretty rough around the edges. We have like weird lines going up and down. Not really something that we expected. What is going on, Thomas? What's up here?
Yeah, let's have a closer look. So if you just put all of these lines together, we end up with something like that, which is, from an art perspective, quite nice, but it will not help us at all if we really want to make sense of that. So we did a Fourier transformation to see the different frequencies that are in there. And the first one that really comes to our mind is this weird spike when it comes to 50 hertz. Yeah, that sounds suspicious. So, yeah, of course, the electric power supply runs on 50 hertz, and so we are now seeing things that are closely related to something that has nothing to do at all with the brain-computer interface. It's just that we have some, electric waves in here. So we should really get rid of that, and we'll let our friend Louis Kane do this for us. In this case, he's not really the fighter from Mortal Kombat, but rather a notch filter, which we applied. And there were also some other cleaning steps, which we needed to do to really get from something that looked like this to something that looked like this. And this looks a bit cooler, doesn't it, Jonas?
Yeah, let's have a look at my brainwaves now. So, as you can see, this is much closer to what we wanted to see and what we saw like in the OpenBCI GUI. And you can even see if I'm like blinking, there's beautiful artifacts in there because, well, contacts get kind of stronger and then we have like weird bugs in there. And you'll see, yeah, it looks kind of good. We could actually work with this. The only issue is, yeah, it's kind of a fake demo. And
the reason for that?
Well, yeah, why is that?
Te llamo para que vaya a recoger las paelleras. Y me acuesto en su, ya para abrir el restaurante que era el arroz. Y me llama el cocinero. Risita, ¿qué? Ve por la paellera. Venga, a las 2 de la tarde ya están aquí. Miren, bañador. En las chanclas. Todo despeinado porque no me dio tiempo nada ponerme las chanclas y el bañador. Voy a la playa, había subido la marea.
Yeah, so that's why we have some beautiful recordings of our last session for you here. So another thing that you could do in theory is have a look at the burger effect. Turns out when you're standing on stage, talking to a lot of people, it's quite hard to relax. So we don't ever really see this dip or this peak in the alpha waves.
So just to go for sure, this is real data from one of the last conferences, and we really did this in a live demonstration. So
yeah.
This is also why Jonas had quite a hard time to relax there.
Yeah, it never really works on stage. Anyways, but now in theory, if we don't lose the dongle and the shipping's like 4 weeks, then we can now read our brainwaves now we can generate signals from that, can't we?
Yeah, that is the question. Now the topic, control signal generation. So, yeah, the idea was that we just take the brain waves, we transform them into control signals and send them to a quadrocopter. So sending the control signals to a quadrocopter is somehow very easy. We did that back in the days. But brainwaves, okay, which brainwaves? How do we record the training data set and stuff like that? So our first idea was, what if we just think of different actions? Like, I'm thinking about a fist, and this could, for example, mean the drone goes up. And if I think of open hand, the drone, I'm recording those brainwaves, and this could mean the control goes down to the bottom. And the idea was just think about it, think of it, and then record the brainwaves and do some pattern matching. Let's have a look to a normal EEG. Here you can see an EEG, where it's taken out of a paper, which is 15 seconds. Yeah? And you can see those brainwaves here from the different channels. Let's have a look to another one. Okay. From the point of view of a computer scientist handling with data, there is a difference between both. Yeah? Okay? Yeah, we can make control signals out of it, or not. But there is a problem. Actually, this is an epileptic seizure EEG here. And this is a problem for us.
That's not very usable, no.
It's not very usable. So what did we then? Here. Yeah, there is a possibility to just read those 1,000 research papers in the fields of neurofeedback, or take the innovation hacking way, try it with AI, artificial intelligence. What was our idea then? The idea was we take the cleaned EEG data and we throw that into a deep neural network. We train it with this cleaned EEG data, where we are thinking about an open hand, a closed hand, and whatever. And yeah, the deep neural network is then telling us the control signal which goes to the quadrocopter. So, how did we start from here?
Yeah, the thing about the innovation hacking team is we are quite good with images. So we know how to use one image and say, this is a cat, this is a tiger, this is a dog, this is a frog, or this is something completely different. So this is the good thing. The bad thing is we don't have any experience with time series data. So our thoughts were, hey, how do we get this thing together? And it's not that easy, so we really need to pack this time series data somehow into a neural network. And actually, there is some research, and the best way to do this at the moment is to really use images. So that was quite handy. So the resulting image is called a so-called Gramian angular field, and what this does is we are taking the time series data, we are just extracting this data, putting this into polar coordinates, and from this we can then create an image with this data, which represents exactly this data as this image which you can see on the right side. And if you scan this QR code, which is currently on display, then you will get to a paper of where this is explained in a lot more detail, actually. Okay, and then we can use all of this information that we now have and put this through our neural networks, which is in this case just a convolutional classification network, as we have done a few times before in one of our last talks. And if you scan that again, you will see how this works for brainwaves in this case as well. Okay, and now that we have that, we can now just take the 16 channels that we get from the BCI. So here you can see real life footage of how the different channels look like as these Gramian angular fields. And then we can use that to train our neural network. So we have the data of someone thinking of a fist or an open hand, and we have at the same time these beautiful images, and now we can just train that, right, Jonas?
Yes. Let's go to the training. Here you can see the output from the tensor board, and you can see we have the blue line, that's our accuracy in the training, and it goes up, and that's good. It's good, right? So that's the accuracy that we're kind of hitting the right control signal. We have 4, up, down, left, right. And everything is nice and dandy until you look at the orange line. Because that's the validation accuracy, like on data that the neural network has not seen. And you can see it's somewhere around 25%. So that's roughly random, which is not good. So what has happened here is that our neural network basically didn't learn anything at all, other than how the training data set looks like, and this is not going to be usable for whatever use case. And we also kind of, while we were at it, noticed it's really annoying to record a data set like this. So there's a little experiment for you guys here in the audience. Try thinking of a closed fist for 20 seconds straight without making a closed fist, and like maintain that concentrated thought. It's not that easy at all. And also that might just not be the most intuitive way to control a drone. So our idea was, okay, why should we not simply control a drone by thinking about controlling a drone? So the idea is simple. We place Jonas on a large controller and let him control a drone, and while he's at it, we record his brain waves, and what we can then do is like train some kind of neural network on those brain waves and the controller inputs to then predict controller inputs. And we wanted to start that, and we'd learned from the past that it's probably not the best idea to fly drones in the office. So we wrote a little snake-like game that looks something like this. It's called Eat and Don't Get Eaten. We put our heart and souls into it, and you can see we have the blue protagonist here going through the very colorful world. And like every other human, his entire life is just like passing from meal to meal while evading the red enemies here. And so we played that for a couple of thousand hours and recorded our brain waves while doing that, and we ended up with a data set that looked like this. So we have our pre-processed EEG data on the left. That is basically what we're going to give as an input to the neural network. And then we have, like, this is control stick data plotted over time that we have as outputs for the neural network. And now we can train that. There's no QR code there. So you see, nobody has ever done anything like it. So the question was, what kind of neural network do we even need for that? And the solution for us was something that is called a genetic algorithm that chooses that architecture of a neural network for us. It's kind of basically evolution, just with neural networks. So what you do is you kind of start up like you would in nature. You take like your first samples, you collect them from nature, and this is going to be neural networks for us with all kinds of different architectures. And what you do then is you select the best ones, and best ones in this case means that they train the best, and that's not for training accuracy, that's for validation accuracy. And you select your best specimen, and then you kind of just let them do their thing, right? They reproduce, and in this case, this means we just clone them or add in a couple of layers every now and then. We mutate them or kind of mix them together. And then we repeat that circle over and over and over again. And after you've spent like $500 on AWS, then you end up with a model that does something like this. We're getting there. Well, let's have a look at the data. So here you can see the accuracy, and it's pretty good. It's in the 90s. The only issue is now we don't have those 4 discrete input signals anymore, up, down, but we have like a continuous controller signal. So what we're kind of plotting here as the accuracy, that's the loss angle, so that's the error angle that we have, which is on average 90 degrees, which is, well, not very good, to say the least, and it's not even good in training. So yeah, at this time, we were kind of very frustrated with just constant coin tosses that went wrong. And we decided, well, maybe we should try something else. But that was not the only problem that we had at this point, right, Martin?
Yeah, we had a lot of problems. And this image pretty sums it up. So there are different types of headache: migraine, hypertension, stress, and wearing the OpenBCI for 5 minutes. Yeah. You might ask yourself why, so let's have a detailed look on this. So as Jonas already showed us, those spiky electrodes, let's have a look how it looks like after the, I would say, 3, 4, 5 minutes. It's good that I'm bald, so I can show you the pain. Yeah. So the question is, what do we do now? OpenBCI or not do OpenBCI? So we had a look, which devices are on the market. So we found this little thing here. It's the EMotive Epoc-X, and it's a 14-channel brainwave device, and it comes with a software which says, you can train different commands with it. And this is the software, how it looks like, and so I tried to train it. So you have this cube here, and then you should think about something. Again, I've started with thinking of a closed hand, an open hand. Then I'm starting to sing a song, and in my mind, or counting 500 backwards in 7 steps, and so on and so on. And to sum it up, I only was able to differentiate between 2 states. The state where I'm doing things in my head, like singing a song, without singing it, or just being relaxed. So in fact, it's differentiating between alpha waves and beta waves somehow. I was not able to train more than 2 states, which is obviously not enough to control a quadrocopter. But we had a look to another device, which is the NextMind.
Yes, in comes the grand NextMind seen on CES 2020, and I saw it and I was like, okay, cool, this might turn around this project which is not going too good. And what it's supposed to be is like a BCI for the masses. And you can see it has a couple of dry electrodes, and it's pretty small, and that's because it only sits on the back of your head. And the way it's supposed to work is like this. So the NextMind, what you think is what you do. And it sits on the back of your head, and back there you have the visual cortex. That's where you see things. So when you're looking at like a triangle, there's just like a picture projected into your brain directly, and somehow the NextMind can decode that. And they're using like AI, sort of, but they're not really telling you what it is. So the main application for this is, of course, gaming. Oh, shoot. And here you can see like a demo video of how you would use this in a typical game. We have a jump and run game. You play it with a controller, but every now and then you have like enemies that you have to kill with your brainwave. And we had a closer look at all these obstacles and enemies that you kind of have to manipulate. And before we have a closer look at that, if there's somebody who's like issues with flashing imagery, something like that, better close your eyes for the next 5 minutes, otherwise your brainwaves might look like this. And we don't want that. Anyways, if you have a closer look, you'll see there's like this strobing pill or virus kind of pattern that's going on all of those objects that we want to manipulate. And actually hurts your head if you look at it for too long. And the interesting thing is we got our hands on this NextMind device, and we opened up the Unity package that it comes with, and we found these beautiful textures that are called stimulation textures. And what happens is you can, in the Unity API, you can just give your game objects a so-called neuro tag, and this will then make that they flash like we saw before. And if we now take these stimulation textures and have a look at the video again, we can see, it's kind of, you can kind of just like fit it in there. It's literally just a texture. There's nothing that's kind of generated randomly. It's all in there. So at this point, we're thinking, is it really the object that kind of creates this huge image at the back of our head? Let's have a closer look. So we created the scene with 3 completely identical cubes, and gave a neuro tag to each of them, and you can see now they're like flashing with the exact same pill pattern. They look exactly the same, And the only way you can differentiate between those is kind of the frequency that they're blinking at. And at this point, knowing everything about EEGs and BCIs that we do, we can make an educated guess, and that is, well, this kind of pill pattern, which is surprisingly exhausting to look at, well, this might just generate like some impulse in the back of our head, in the visual cortex, that we can then measure with something like this. And then depending on the frequency that we have, we can decide which game object it is that we're looking at. So what does this mean for controlling drones? Well, we can only kind of differentiate between things that are in-game. So we could build something like this, a controller that you will stare at, and you'll stare at like the left thing for 5 seconds, and then it will eventually register that you want to fly left. And you're not looking at the drone, and it kind of really doesn't work. Like, this thing is cool. This thing is cool. You can do heaps of stuff with it, but probably not fly a drone. So that's 3 fails. What can you actually do with this, Thomas?
Yeah, at this point we were quite disappointed. But there are different fields of application that are in theory possible. So, of course, there's the medical application, and this is the most obvious one. But you can also use it for neuroergonomics, so that you can say, okay, this feels good, or this chair feels good, or this chair feels awesome. And then you can measure that, and you can also do it for marketing research as well, and advertisement, so that you can really check whether your marketing campaign goes well. On the more traditional side, we'll have something like self-regulation, which could work quite well, and games and entertainment, we just saw that. And also, at least in theory, it could be possible, based on your brainwaves, to unlock your device or things like that. The only thing that we saw that really worked was this device, and again we have something which measures whether you are relaxed or not. So this is kind of a pattern here. So it's for sleep tracking, it's for meditation, it's called Muse, and you use it for, of course, the same effect that we had a few times here, the Berger effect, with which you can check whether you are really relaxed with alpha waves, and beta waves if you are not so relaxed. And this might actually help you, but not in the way we imagined it to be when we started the project. So let's get to the conclusion, Jonas.
Yeah, my first project at TNG, yay. Like, I was coming in with really high expectations. They were not really met, let's put it that way. So we had a bunch of issues. So obviously we had headaches all the time. We lost dongles. The hardware was really bad. You might have noticed in the demo we only have 8 channels because the other ones are broken. And in the end, it just comes down to we don't have medical accuracy, and there's no way of NOMOX actually going on in the head without drilling holes in it, which Thomas for some reason doesn't want to do. So all of this kind of gave us the confidence to be like, okay, you see there's brain-computer interfaces in the Gartner hype cycle. Let's just kick him out of there. And well, if you look at the Gartner hype cycle for the next year, you can see, well, it's not there anymore. We did a good job, but it's kind of there a couple of steps further back. It's now called a two-way brain-machine interface, and it's kind of evolving, but backwards. So what's the bottom line here, Thomas?
Yeah, so the bottom line after all these experiments is that we really don't see the potential right now for a non-invasive BCI to be able to perform such detailed tasks. So this is probably not possible with the consumer electronics that we get today. It is somehow possible if you just use invasive BCIs, so then you can do things like the ape did. So this was actually some kind of invasive BCI that was used there. But yeah, nobody wants to really drill holes into your skull, and this is I think that's common sense, isn't it? Okay, so with that, we've now come to the end of our talk. And if you want to know a little bit more about our other talks from the last few years, we have Style Transfer AI, where you can see the world through the eyes of an artist, and we also have the real-time deepfakes. These were actually successful projects. And yeah, just photograph the QR codes if you want to know more.
Yeah.
And now, if you want to know more, there's also questions, and we have exactly 5 minutes.
5 minutes left, yeah. We can ask your question if you like.
All right, do we have a mic? No.
Do we have a mic?
He's just going to have to scream all the way in the back.
Is it actually possible to get an implant as a consumer? Because I don't want one right now, but maybe when I'm 80, or if I terminal illness and 2 years to live, then it might be cool to experiment.
Yeah, that's definitely an interesting, question. We don't do that, but you might have to call up Elon. No, they do clinical trials mostly for people who are not capable to use like their normal limbs normally. But however, I think that might just be more of a thing in the future. However, we don't do that, and we don't personally know anybody who would do that either.
Yeah, and at the same time, we have not researched that, but it might be possible to also take a part in this medical trials. Who was next? Yeah.
Well, first, some marketing here. If you want to try the Emotiv, just to move some box, something like that, and see how complex it is, you can go to the stand of Accenture Little Studio. We have a couple of them. We've been playing with them for a while as well. So you can try it there later, so you can really feel it. And then my question for you is, do you see in the coming future something that the EEG waves can fit anyone? Because right now you have to try to train the model for each different person, because brain waves based on the person are totally different.
Yeah, so I'm just going to repeat the question. The question was, do we see a future where EEGs are just going to work for everyone? Because now it's like you have to train a model for a specific person. That is true. To be honest, at some point it might just be there. We've seen this trend in AI that we came from overfitting to like a single sample to being very much able to generalize. However, this is not so much the case with the kind of hardware that we have right now, with the non-invasive BCIs being very prone to noise, and the invasive ones, well, every brain is kind of different, so we'll kind of have to come up with a solution for that, but we're not seeing that on the horizon just yet.
Yeah. Here were a few questions,
yeah.
So here, please.
Guy on the right.
And then you.
Our right.
Your colleague had something against drilling holes in his skull. But
Right.
what about if you tap motor neurons in other parts of your body? For instance, physical therapists are using techniques called dry needling, where they stick acupuncture needles into the muscles.
Mm-hmm.
So let's say you get an arm, so acupuncture needles, and you tap the motor neurons there. So you don't have to drill holes in his head.
Yeah, that's a very good question. So the question was, why go into the brain? You can just tap the nerves somewhere else. And I think we do have a couple of backup slides for that. And yeah, and we see that here. Like you can actually do that, and this is also widely done in like prosthetics. Going into the nerves, like somewhere where the signal has been processed by the brain, that makes it way easier. And there's actually also not only acupuncture needles that you can stick into the nerves, but also like pads that you can have on the surface that are basically going to work the same way as a non-invasive BCI, but just for like nerve signals. So that is done today. It works quite well for amputees. The big issue is usually if you have nerves that are kind of transferring some kind of signal, that already has a purpose. So what you could do, for example, is like have a second hand on top that does exactly the same as the first hand. Yeah, that was not really what we were intending to do.
Did you guys compare the signals between devices? Was the pain worth it for the OpenBCI?
So just repeating the question, was the BCI, the OpenBCI worth the pain? And did we compare signals between devices? Very interesting questions, because all of these different devices have very different policies when it comes to how the data is read and how it's made available to the user. So for example, the NextMind doesn't give you any access to the data whatsoever. It just gives you like the access through the neurotag thing.
Yeah. For Emotive Epoc-X, you actually can buy a license that you can access the raw data, for example. And in comparison to the OpenBCI, these are wet electrodes. So you have to put some kind of a fluid on it so that it will work. Our first decision actually was for OpenBCI because of different reasons. So using wet electrodes when the project is successful was not what we want, because the idea was that we are on conferences and everybody just wears the helmet and controls the drone. This was the basic idea, but yeah.
Yeah, but to sum up the question, we don't get any kind of raw data from the NextMind. We could get it from the Epoc-X, but what's the point if even their software doesn't work? And then for the OpenBCI, well, you get data, it's quite noisy and it hurts a lot.
Yeah, so it's 3:30. One question, one last question? No?
Yeah, back there.
Back there.
Okay.
How long does it take to train one of these requests?
So I'll repeat the question. How long does it take to train? Do you mean like for the Epoc-X or for the models that we showed? Okay, so for the Epoc-X, that's actually the long part is generating the data, I believe.
Yeah, I made several trainings, but the problem is also with the Epoc-X, the fatigue. So you will get tired of it after a few minutes. So training for 15 to 30 minutes, it's a real thing, to be honest. So and that makes it very complicated.
Yeah. But I think for the Epoc-X, the training itself, so the optimizing of the model that is done by the computer, that happens quite quickly. That happens kind of on the go. Whereas for a neural network, as we're using them for the OpenBCI, the training was like, you could tell a definite trend after half an hour.
Yeah. I want to add something. So when you are using the Epoc-X software, for example, and you are looking to this cube I just showed you, this one particular session is only a few seconds. Let's say 10 seconds, 15 seconds. But typically, you do a long training session with different mini sessions, you know, to get a trend, to differentiate between actions. And so I tried it for 30 minutes and I was totally tired of it. Yeah. Okay.
All right.
So that's it.
Thanks for your attention. Thanks, J.
Yeah.
See you next year.
Thank you.